Our speakers are from Athena Health. We have Sham Mandabi, and he's currently the senior architect of the Athena intelligence team. Prior to Athena, he led the analytics and big data team at Kronos. We have Karthik Urs, and he's been with Athena Health for a little over 2 years and currently leads the back-end engineering efforts towards analytics of healthcare data. And Ramesh Kampana, and he's currently the PMTS of the Athena intelligence team. He leads the effort in creating the cloud infrastructure for Athena intelligence process. So without further ado, let's hear from the Athena Health team around automating CI and CD for Druid clusters. Take it away, guys.
Morning, this is Sham Mandabi, and I'll sort of start off our presentation, and then we'll go through and hand off to Karthik, who will explain, our sort of Druid architecture at Athena, and then Ramesh will do the heart of the presentation, where he'll discuss the actual implementation of our CI/CD process and how we automated deployment of Druid into our AWS infrastructure. So, so the overview, basically we'll talk about the goals, as I said, Druid architecture, and why we chose some of the deployment tools like Terraform, and then go on about, talk about CI/CD process. So let's, just a little bit about Athena, I guess, before we go on, just in case. Basically, Athena Health is software as a service provider for medical practices. We provide sort of, as well as sort of a unique combination of back office operations as well. So we have a lot of data that we get. We probably provide services to support about 15% of the American population in terms of medical services, both electronic health records and claims management. And so there's a lot of data that we collect and a lot of data that we can analyze in order to help our medical practices and our doctors essentially, as our motto in Athena Health is let doctors be doctors, right? So make sure that they spend the least amount of time, but also are appropriately remunerated and get their claims processed and help their patients as best as they can. So, so basically, at what we're building at Athena Health using Druid is really an internal application which will be going external to analyze essentially all our different claims data as well as our healthcare data. So with that introduction, let me go to our sort of reasons about next slide to talk about what, how we came to choose Druid as one of our tools for our analytical environment. So, I think as I talked about, what we're trying to power here is a sort of a self-service analytics environment for both internal and external customers. We are we're not in production. We're still, at the sort of alpha phase of this deployment. So we're still not scaled up to our complete, data volumes that we expect to be supporting. But we do, when we scale up, we do expect to have, thousands of our customers and our business analysts, both internal and external, using these new dashboards we're creating to answer key questions about their business and sort of get insights. So with that in mind, so the key features that we need to support from our platform was, it's really low latency and subsequent response. And of course, that meant that it had to be horizontally scalable. A lot of the, sort of the questions asked from medical practitioners or medical business analysts have a lot of different dimensions, right? And they look at, CPT codes, procedure codes. They'll look at different insurance providers. They'll look at the actual conditions. So a lot of different variables that they'd want to, question the data on. And for that, we really needed something that would support that high level of dimensionality. So we looked at a couple of alternatives as we looked at this, and we settled on Druid mainly for these reasons I've listed out here. We do also have in our environment Snowflake, which is the integral part of our sort of our analytics and warehousing space, and it's a great database. But in terms of the aspects about really the high level of concurrency and latency and low latency we needed, we felt, and based on some experimentation, we felt that Druid would support that better. And Snowflake is really part of our chain where we sort of feed data into Snowflake, and then from there, load data into Druid. We did look at Cassandra as well, and again, that's part of our ecosystem, but we felt that given the dimensionality of the data, trying to use Cassandra would lead to a high degree of replication, and hence leading our pipelines to be a lot slower when loading data on a daily or hourly basis. So today we are actually using Druid in a more sort of batch manner, but we do in the future expect to have more real-time data, which is another rationale, a reason to go to Druid. With that, let me hand off to Karthik to talk about our sort of infrastructure and Druid at Athena Health, and also some of the reasons why we invested in essentially automating a deployment of Druid. Karthik?
Yeah, thank you, Shyam. So, hey guys, this is Karthik. So I just want to quickly run through the architecture we have for Druid. So we have deployed the whole Druid cluster on AWS. What you typically see here is what you would be used to at this point. We have master nodes and we have query nodes. But one thing what we've done separate is to break the data into its own separate processes, like historical and middle manager nodes, their own separate nodes. So I'll talk about this why later, but quickly it's just to make sure that we have easy route to scaling each of these services separately. So in terms of deep storage, we're using S3 and we're using Postgres as a metadata store. And Zookeeper is something that we have a separate infrastructure around, and we are maintaining our own Druid Zookeeper cluster. So quickly, if we can go to the next slide. So this is what our cluster looks like right now. So we have 3 separate abstractions of environments. So we have a demo/dev environment, and we have staging, and we have prod. So what you're seeing here is the number of nodes we have just to work with initially. Like Shyam was saying, we have very less amount of data that we have right now. We have less than 5–10% of data that we can potentially go to. So in the dev environment, we have no SLAs, it's strictly for development purposes. So we have a smaller cluster. On staging, we are pushing up some of the more refined workflows into staging environment. So we have a fairly larger cluster size here. So what we do is we scale the middle manager nodes to 20 instances of staging when the ETL is happening. So we do batch mode, batch ingestion. So when the ETL is happening, we scale it up to 20 nodes and scale it down once it's done. On prod, it's more SLAs are more strict. So we scale it up to 50 nodes just to make sure that ETL is done faster. With this overall cluster, I want to talk about some of the motivations that we had to invest time and effort into building our own CI/CD pipeline. If you can go to the next slide. We are in the pre-alpha stage right now, so we do a lot of POCs and a lot of performance testing. So what that leads us to is to build and destroy Druid clusters on a very frequent basis. So we are also evaluating Druid, new versions of Druid as it comes out. So we do a lot of build and destroy. So we needed an automated way to do that without spending too much dev time into this build and destroy process. And another one is the scaling above Druid clusters also had a lot of semi-manual work. We did have some CloudFormation templates for AWS to bring up the machines and to do some of the stuff. But we do work with different types of instances for different nodes and environments. And the tuning of JVM strictly depends on the vCPUs and memory that we have on Druid, at least at the very high level. So we wanted to automate that process also. So we wanted to be able to build the configs during runtime instead of having a separate process to do that separately. And also for the dev environment, we have debugging enabled, the log level is set to debug. So we do spew out a lot of logs. Having the flexibility to pick the different APS volumes in terms of storage for log before it's laid down into the deep storage is one of the things that we also wanted. Another key thing is the governance around the infra that we have. So be it in terms of the security group configurations or the AMIs that we use, we wanted to inherit the governance that we have with the centralized AWS team. So we wanted automation for that purpose also. And also we wanted to have some monitoring and alerting capabilities. So we have an element stack and we wanted to feed into the element stack that we have. So right now the scaling of middle managers is done separately through a service which is listening to the Druid clusters through a Lambda, and it knows when to scale it up and scale it down based on the tasks that are in pending state. But we wanted to have the metrics tie into the whole upscale and downscale mechanism. So we should be able to scale up a broker node separately if and when the time comes. So these are the main motivations to invest time into the CI/CD pipeline that we have. I would like to hand it over to Ramesh, and he will explain more about what goes behind the CI/CD world. Ramesh?
Hey, thanks, Karthik. Yep. So given these requirements from the dev team, so we had to make sure the entire process is automated and get any size of Druid cluster. So so we had to shortlist the tools which we leverage. And in Athena for infrastructure as a code, we were using Terraform. And so Terraform is a pretty tool available in the market, and it's a community supported tool. And so on the feature sets which we really like on Terraform is it clearly separates on the plan from the execution part. And it supports multiple cloud providers, although we do work with just AWS, but we do extend with other tools like NS1 and other things. So this integration really helps us to work with one single tool. Also, we could leverage adding of existing resources to the existing code, which we could not do with the CloudFormation and other things. If the resources are already created, you cannot inherit that in the stacks, but Terraform would allow that to be incorporated. Also, the code could be modularly written, and so that is going to help us in using or reducing the code if at all code is shared across multiple projects. And also, whenever we run, it's always like Terraform would always say about the real state available on AWS and then give us a diff between that. So the drift is always known, and it's a near real time whenever we try to apply Terraform. But yeah, Terraform also with Terraform, there's equally a set of challenge that you would have to take care of the state management by yourself and get things rolling. So that is where we had built our own in-house tool, and that is called as Buddy. So this Buddy tool helps us in creating new environments and then writing a consistent state file and also the variable files, which will be applied to the Terraform code at any point of time. So at any point of time, even though the repo would have nearly all of these environments, maybe dev, staging, prod, and other things, we can always switch between all of these environments using this Buddy tool, and it would pre-populate between the prerequisites and the state management files and the locking mechanism of Terraform, and also only invoke only the appropriate variable file, which can get invoked for that cluster. Right. So with that, let me go on the entire end-to-end what happens for this cluster to be created. So we always have code, infrastructure as code in our Bitbucket repos. And so Jenkins would is the guy who would execute in our CI/CD process. So this guy, he checks out code, and then he's going to prep up the Terraform, and then he's going to invoke Buddy and switch into the environment which we are going to try to create. And then once we kick off the Jenkins, so it is going to complete all the entire deployment and then throw us a dashboard link. And then from that dashboard link, we can get to the cluster and try to get to our stuff, right? So now let me go on a detailed step of what happens in the all beyond the stages, right? So when Jenkins kicking in, so we have a two set of stages. One is the prerequisites and the main Druid class creation. So as part of the prerequisites, we create the metadata store, which is the PostgreSQL. And there's a S3 bucket, which is used for the deep store. So these two get created. And then we have a bunch of code which just does, it pulls from the repo and creates a tarzi file and then uploads that to the S3 bucket, which was created. And then we do have a Lambda script, which would go and log into the metadata base and create the database and user and a password so that we can log into that database. Right. So post that, then the Terraform is going to kick off and create the main Druid cluster. So it's basically a Zookeeper cluster, which gets kicked off, and then correspondingly all the 4 different clusters which we saw in the architecture. And we also create an application load balancer, and then we would have a target group for the router service to be behind that target group. And yeah, so moving on and then saying like what would happen with each cluster creation, right? So the Druid clusters, as we said, the Terraform is so modular, we could just write one single module for the entire Druid service. and it would take care based on the instance type and whatever service needs to be run, and then initialize that. So this process goes into two phases. One is the cloud init stage. In the cloud init stage, we initially do the OS dependency package installation, like the Java, Perl, and other things which you need as a dependency. And then it based on the instance type and the service type. By service type, we mean non-data type or a data type of node, especially the historical node. In this case, we would need storage disk to be also attached, and also try to prep that and create a data directory along with the normal log folder directory. So when the cloud init runs, so it would identify based on the instance type. We do have different layouts types which we have defined, because we run everything in AWS. So based on the T3, we have a different disk layout type. When we see M5, it is a different layout type, while if it's an I3 comes with its own hard disk, so it can use that hard disk itself to create a data directory and a log directory. So those disk layout types gets automatically assigned based on the disk instance type. So it formats the disk and configures the disk, then formats the partitions, and then mounts the partitions to the respective directory folders. And then it moves to the second stage where a boot shell script gets run. And this initially the Druid binaries get downloaded from the Apache binary archives, and then we download the config file from the S3 bucket, which was uploaded previously. And then we also, in the config file, Tarzi file, when we unwrap that or unbundle that, we will also have binary scripts, which are all basically supervisor related scripts which will execute. So these binaries are also copied to the binary folder. And then on the config files, so based on the resources available on each of those instances, right? So based on instance type, the CPU, RAM, and storage size will all vary. And then based on that, we will calculate what values to be changed on per config files. And then based on service, what is going to run on that very specific config for that also gets changed. So we go and calculate all of that, and then post that we do that install of FileBeat for and a log forwarder. So we use Prometheus for the monitoring, and FileBeat which is going to be the log forwarder, and it sends to the ELK stack for that. And based on the service name which is passed to the Druid from the Terraform, so we just invoke the appropriate start script via this, which is the supervisor script. And the supervisor will keep that service running all the time. So now I think enough of all the talks. So let's see how the entire process happens on a CI/CD flow. Right. So this is a automated and recorded session, at least. So I just have 1.5 minute video. But the actual create takes nearly 7 to 8 minutes to create a testbed on the CI/CD to get the dashboard link, while it takes 2 minutes for the Zookeeper cluster to get into a quorum, and then 2 to 3 minutes at least, and then at least every Druid service node, it takes 2 minutes once the Zookeeper comes up to go and connect to them and get their configs updated. And so overall, it takes 5 minutes for the entire cluster to stabilize and then come back. And as you can see, whenever this code runs, so it would ask for a confirmation, because we need to make sure what are all the resources gets created. We get the entire dump of that from Terraform, and then only once you confirm that, you would proceed to create that. And this is the dashboard URL, which gets spit out post the entire cluster creation. So this is the dashboard URL, and then like in this case of when we created this setup, this was a demo setup, and it has all single nodes, and all these services are going to run. At least we had 4 clusters, and then historical is the data node, which gets its own storage. In this case, we just use an i3. i3 has its own hard disk, which is of 490 GB, and that is what is got configured here. And the remaining space is configured for a log folder. So yeah, so that was the entire create process for Druid. So, but how do we do and any update and other things. So this is all done easily because we just have one variable file for the entire Druid cluster. So we just go to the variable file in Terraform and update the cluster size. Especially here, if it's a Zookeeper, we can experiment with the different odd number of nodes. And the other Druid clusters, we always keep them with the, we just keep them with the instance types and the number of nodes which we need. And also over and above this, what we did is like to bring the costs down for the different environments. We also support, try to create hybrid set of clusters, which can be provisioned via spot instances or on demand. So that is a percentile which we try to configure here. And then whenever we say 100%, the instances are all created via on-demand procurement. And so they'll be always available, while the other instances will be via spot. And we always try to provide the logs size, the log storage size, and even the data size also. So we can always experiment with those data sizes also, the disk size. And these are all mounted dynamically whenever the instance is created. And as a matter of fact, so if at all we want to always update, we just change the variable file, commit the code back to the Bitbucket, and then we can use the same process to go and say env create or update, and then get to the process. So it's gonna go and update the cluster, and that's it. So most of the time, this is all on demand. We don't do any auto scaling as such. Only the ETL process is one thing which is gonna scale based on a pipeline where when we have the real data available for the ETL pipeline to run. So there is a message which is kicked off to an SQS queue, and then that in turn picks up a Lambda, and that Lambda is gonna pick up the appropriate auto-scaling group and then scale it according to these numbers when the data is available. And then once the job is done, it's again, SQS queue message is popped in, and then it's gonna kick off the Lambda, which is gonna do a scale down event. Yep, so this is the overall scale up and scale down and cluster creation back in Athena.
Yeah, so I think overall, I think we found it useful in our environment, especially because of the volatility and especially in the development environment, to have this process that's integrated into our sort of CI/CD process of setting up and committing code and getting developers much more productive going forward. There are, I think, obviously, when we actually go truly into production, you obviously cannot just scale down nodes arbitrarily. We do see in production that we would use this sort of mechanism to certainly scale up and scale down our ETL ingestion processes, especially because we know exactly the time periods and we need those, and also scale up the middle managers, et cetera, based on need. Karthik, I guess you might want to comment on that as well.
That's good, Jim. Yeah.
Okay. So at this point, I guess there's some questions, right, Rachel?
There's a lot of questions out there, actually.
Yes. Right.
Wow. So where do we start? How do you do downgrades gracefully? So what happens when the running request on the historical node when you terminate by Terraform?
So we don't have automatic scaling up and scaling down of historical nodes, just for the same very reason. So right now we only scale up the middle manager nodes automatically because that's tied strictly to the ETL process. So we just have the leeway to scale up the peon workers as much as possible and downscale them without affecting anything else. But the broker and the historical nodes we're not touching right now. For historical, we want to be able to do more, or we want to have more control over things like the segment sizes. We want it to be in a sweet spot that Druid recommends. And we want to see how caching would be impacted. We want to see how the lookups would be impacted. So scaling up and down of historical node is something that we want to do in the maintenance window, at least for now. But broker is something that we want to do based on the logging and monitoring that we are building. So we want the statistics like the request per minute tying to the feedback loop into scaling our broker nodes. And middle managers, we need to see, or we don't have a strategy yet on how to scale it up and down when we do real-time ingestion. But for batch, we have a separate process running, which is completely decoupled with the ETL framework. which basically reads the number of running or pending jobs. And based on that, it just scales it up or down. So as and when the node is done, it just scales it down at that particular instance, which is not being used anymore.
And how do you monitor your Druid cluster?
So right now we have a elk stack built around it. So we are building a Kibana dashboard. So a part of the monitoring was done through CloudWatch logs in the dashboards, but we're moving away from them to a more Kibana-based dashboards. So we are done through the tough part of pushing the logs from AWS to Elasticsearch. And now only thing that we need to do is build Kibana dashboards and tie into the whole alerting framework that's built in.
So you guys mentioned earlier that you looked at Snowflake and Cassandra for this. Somebody had asked whether or not you looked at Pinot or Presto. Can you talk a little bit?
Yeah, I mean, originally, we are, we were quite, AWS centric, and one of the things that attracted us to Druid was its deep storage support on S3 that is built in. I think both, we certainly are familiar with Pinot and Presto and sort of their big data origins. They're obviously, have a lot of built-in support for things like Hadoop, which we actually skipped that and never got into, using that as a storage layer. And so in some sense, we skipped a generation there.
Did you guys do any performance benchmarking between those systems?
No, we did not actually do performance benchmarking. We did, that's what the systems I mentioned is what we actually did, true performance tests against and scalability, and looking in from perspective of, obviously not just performance, but also, cost and maintainability are also part of the aspect when you look at any solution. So Snowflake was obviously very attractive from perspective of, as a service, and maintaining as a service, as well as, of course, the scale aspect. But as I said, from dimensionality and latency, we felt, we needed a solution that give us, I guess, more flexibility in terms of where we could actually do, how much we could cache, and in a memory size we could use, et cetera.
And so why Terraform and not a Druid operator SDK?
Yeah, so really, as I said, the modularity and also trying to work with the existing configuration available. So we did not want to use any new tools, rather using existing tools itself. So that is also one criteria.
And then on top of that, then why'd you build the Buddy tool instead of using the Terraform workspace?
The Buddy tool is just it's a complementary one, which is just managing the state for Terraform. Others, you have to just keep multiple folders and structures and worry about that.
And then the last of that is, then why don't you use Kubernetes?
Yeah, so yeah, maybe Kubernetes in the future, but right now we are not there.
Okay, you guys have a lot of questions, so I'm trying to find ones that are. What are the key metrics you use to scale up and down your Druid middle managers? And then a follow up to that one is why just scaling up and down the middle managers and not the rest of the server types?
Yeah, so right now we're, since this is batch, we are strictly looking at the number of tasks that are stuck in pending state and waiting to scale it up or down. So this is more of a direct feedback that we have, that there are more jobs waiting, so we just need to add more nodes. So we're still building more intelligence to it. So we are not monitoring the CPU utilization and the memory utilization of the middle manager nodes, which might mean that the size of the files that we are ingesting might be larger than what the memory could handle. So those kinds of things is something that we're not touching right now. And historical and broker, we are still doing some performance testing. We don't know what concurrency numbers are and what concurrency we can push with the different flavors of clusters that we have right now. So once that data is prepped and once we have more insights into what our concurrency scenario is, we would then try to see how to scale the brokers separately. As to historicals, like I said earlier, we need to understand more about the type of data we bring in and how the cardinality of that data directly translate into size of segments. And there are other things that are more intricate in terms of segregating different customers' data into its own separate buckets. So once those things are figured out, I think we'll have more clear path towards scaling historical nodes. So until then, we are making a conscious effort not to touch the scaling of historicals.
Are you required to separate data from different customers? And if so, how do you separate the data so they're not stored on the same data node?
So right now we don't have any segregation. So we have the authentication. We have several other layers which come behind Druid, which does a lot of authentication and authorization. So the Athena RC framework would make sure that the scope of data that we're looking at is very narrow. But that having said, we are making a call as to whether to have all the data across different customers coexist into the same cluster or same data source even, or break them down into different data sources or different clusters.
Yeah, so I think that's part of that would be obviously we will segregate customers where we need to do that based on sort of legal constraints, right? That's one aspect of it. The other aspect is performance, right? Ideally, and scale where we look at it. So typically we would expect that we would segregate customers as necessary, and no one could as you said could see a set of customers' data across that. Right?
A couple people have asked whether or not your buddy tool is open sourced.
No, it's not.
Not at the moment, anyway. Yeah.
And how do you set your performance metrics? Do you have SLAs or?
So yeah, so the front-end team, the team that builds the front-end on Druid, they have separate SLAs for different types of dashboards, and the reporting framework has its own separate SLAs. So SLAs is something that the other team defines, and we try to tune the Druid cluster to meet those SLAs in terms of query performance.
Yeah, so we're very driven by, I think, by end user performance here.
Well, thank you guys so much for the presentation and for answering all the questions. There's still 14 open questions, so we'll be sending those over to you guys to answer, hopefully in a future blog post, because there's some really good questions in here that we just didn't get a chance to get to. But thank you guys again. This is an incredibly cool project, and we really appreciate you telling us all about it.
Thank you.
Sure, you're welcome.
Thank you.
Thank you.